What's up guys, welcome to part 1 of my video series called Level 7 in 7 hours, where I give you a complete tutorial on an IB subject within 7 hours. This will be an 8-part series covering the entire IB Computer Science syllabus for 2025. This video will cover topic A1 called Computer Fundamentals. Now there's 4 subtopics inside of A1, and the first one, A1.1, is called Computer Hardware and Operation. We'll be covering these 5 sections throughout the subtopic. To start off, these are the different components of a computer. Inside of every laptop and desktop, you'll find these components to be in every single one of them. Here's a diagrammatic version of these components inside of a computer. We'll cover each one of them in detail, and by the end, you'll have a good understanding of how the computer works. So let's start with the CPU. So what does a CPU even do? I'm sure you've heard by now that the CPU is the brain of the computer, which would be correct. The CPU executes instructions, which are basically calculations and logical decisions that keep the computer running. To do this, the CPU is made up of multiple different components listed here, and we will get into what each component does in a bit. This diagram shows how the components of the CPU are laid out. The CPU gets its instructions from RAM and loops through a cycle called the fetch, decode, execute cycle. We'll talk about RAM in more detail later, but simply put, in this cycle, the CPU fetches an instruction from RAM, decodes the instruction, executes the instruction, and repeats the cycle for the next instruction of RAM. Let's say that in RAM, there's an instruction to add 2 memory locations together. So here we can denote this by saying add 2, 3, where 2 and 3 are just these memory locations. And let's just say memory location 2 has 6 and location 3 has 8. So how does the CPU execute this instruction? Firstly, it needs to fetch this instruction into the CPU, and let's see how it does that. So firstly, this register called the program counter updates its value to hold the address of the next instruction to be executed in RAM. So here, because it's stored in location 1, we'll have a 1 here. And now this value is copied into the MAR, or memory address register. Now what the memory address register does is it holds a memory location that the address bus needs to go to. And what the address bus is, it's just a wire that sends signals to RAM that indicates that something needs to be done with that memory location. So a signal now is sent through the address bus, and it basically tells the RAM, yo, we need something from memory location 1. And now the data from RAM is then sent through the data bus instead. And so this instruction is put into the MDR now. So the MDR holds add 2, 3. And now this is then put into the CIR, or the current instruction register, because this is the current instruction that we're running. So the CIR will now hold this value. Now that's the fetch portion of the fetch, decode, execute cycle done. But now we need to decode this instruction, because so far the CPU has no idea what add 2, 3 actually means. So how is this instruction decoded? Well, this instruction is then sent to this control unit. So the control unit has add 2, 3. Now, one function of the control unit is to decode instructions and understand what they're saying. So here, the CU now understands that these 2 memory locations need to be added together by, let's say, the arithmetic and logic unit. Now the execution stage begins. Another job of the CU is to coordinate the different parts of the CPU. It does this by sending control signals through these wires called control buses. In a way, the CU can be seen as in charge of the execute phase. So how does the CU execute this instruction right here? So now the CU understands that in order to execute this instruction, we need to get the data from memory locations 2 and 3. So what it does is it sets the MAR to location 2, and then the same thing happens. A signal is sent through the address bus, and then the data is sent back through the data bus, and the MDR is then updated to 6. Now this 6 is then sent to the ALU right here, because the ALU will be in charge of adding these 2 numbers together. So now the ALU has the number 6. Now we need the data from location 3, so the MAR is then set to location 3. Now the address bus goes through, there's a signal through the address bus, and then the number 8 is then sent throughout the data bus, and this gets updated to 8. Now the MDR gets updated to 8, which is then sent again to the ALU. And now the ALU with these two numbers can add them together to get the result. And now with this result, it needs to be stored somewhere, which is where this register comes in, the ACC or accumulator. So it's then sent over here where it's set as 14. And there we go. That's one instruction done right there. Now let's talk about how we can increase the speed of this fetch, decode, execute cycle. One way is through cache memory. Cache memory stores recently used data and instructions, and every time the CPU wants something from RAM, it checks cache first. Say for example that we have the same instructions, add 2, 3, 6, and 8 here. After this process has been completed, all of these are then added into cache right here. So add 2, 3, 6, and 8 are then stored inside of cache. The reason it does this is because cache is way faster to access than RAM. So if the CPU can get what it wants from cache, it'll take shorter time to fetch. If what the CPU wanted is in cache, it's called a cache hit, and if not, it's called a cache miss. So let's say that in a future instruction, the CPU needed the data from memory location 2. Well, it's in RAM, but it's also in cache as well. So that would be a cache hit because it can just retrieve the data from here rather than have to go all the way towards RAM. It's not directly shown here, but cache is actually split into 3 levels: level 1, level 2, and level 3 cache. As a level gets higher, the access time gets longer, but the size generally increases. Another way to speed up the CPU is through multi-core architecture. Oh, and here's the different levels of cache right here. The collection of the registers, the ALU, and the CU make up one core, like so. And this bundle right here is basically a mini CPU. You can make several of these collections and put them in the CPU, essentially allowing 2 fetch, decode, execute cycles to happen in parallel. A CPU which incorporates this is called a multi-core processor, and they're widely used today for almost all processors on the market. Another more complicated way to increase the speed of the cycle is through pipelining. If you had a keen eye, you'd notice that while an instruction was being executed, for example, by the ALU, all the components to fetch or decode an instruction were idle. So these registers were idle and the control unit was also idle. By pipelining, we can make the CPU do everything at the same time. So while an instruction is being executed, the next instruction can be decoded and the next instruction can start to be fetched. This might all sound a little confusing, but this diagram should clear things up for you. Let's assume each step of fetch, decode, and execute take up 1 unit of time each. In the first time block, instruction 1 is getting fetched. In the second block, while instruction 1 is getting decoded after getting fetched, instruction 2 is now getting fetched. In the third time block, instruction 1 is now getting executed, instruction 2 is getting decoded, and instruction 3 is now getting fetched. And this cycle continues for each time block. One new thing in pipelining though is this W right here. This stands for write back, and it just means store whatever it calculated in the execute stage and put it back into RAM. This ensures that data is written back into RAM in time for future instructions. So even if instruction 2 needed to execute something based on the result of instruction 1, it would have access to it by the time instruction 2 was up for execution. And notice how without pipelining, executing these 5 instructions right here would have taken 15 time blocks in total because, of course, 3 times 5 is 15. But here, it only takes a total of 8 time blocks. That's basically everything about the CPU that you need to know. Now, let's talk about the GPU. The GPU is a coprocessor to the CPU, meaning the GPU shares some of the burden the CPU is under. This means that the GPU also performs calculations and logical decisions much like the CPU. The difference is that the GPU is much more suited for parallel processing and intensive computations, such as 3D graphics rendering, video processing, simulations, crypto mining, and machine learning. So how exactly is the GPU better at parallel processing? Well, the GPU kind of looks like this. Each one of these squares that you see is a core. Each square has its own ALU, CU, registers, and cache, much like a core in a CPU. You can think of this as like an assembly line of workers instead of just a skilled craftsman like the CPU. Due to this, the GPU can split up complex tasks into many small parts for each core, and carry them out simultaneously, making it much more suited for intense computations than the CPU. It's worth mentioning though that each core in a GPU is way less powerful than a CPU core. This means that the CPU is more suited for handling more general and lightweight tasks, while it offloads the more complex and computationally intensive tasks for the GPU to handle. So far, we've covered the CPU and the GPU, but we haven't really understood where these instructions for the CPU and GPU are coming from yet. That's where RAM, ROM, and secondary memory come in. These are all forms of memory. There's different kinds of memory. First is primary memory, which is memory that is directly accessible by the CPU. If you look back at this computer diagram, you can see RAM and ROM linked to the CPU, making them primary memory. Registers such as the MAR, MDR, or cache also count as they store information as well, making them memory. We've seen RAM, registers, and cache before, but what exactly is ROM? Here's a pseudo-Venn diagram explaining both RAM and ROM and their differences. So we've seen that RAM holds instructions for the CPU to execute, specifically from programs. These programs can be anything, from apps, to games, to Windows itself. While ROM also holds instructions for the CPU, ROM holds something entirely different from apps or games. It holds essential instructions for the computer to boot, also known as the Basic Input-Output System, or BIOS. While RAM's contents can be read from and edited by other computer parts, ROM's contents are read-only. Also, when the computer is turned off, RAM's contents are lost, while ROM's contents are preserved, of course to boot up the computer again. The other kind of memory is secondary memory. Secondary memory isn't directly connected to the CPU. It holds program data and files, and unlike RAM, it retains its data when power is cut off. There are a lot of different types of secondary memory. So we'll first look at internal secondary memory. This is memory that is more or less glued to the device it was originally connected to. First is a solid-state drive, or SSD, which uses stored electrical charge to store data. Next is a hard drive, or HDD, which uses a magnetic spindle to magnetize certain parts of the rotating disk. Both SSDs and HDDs are commonly found in computers, and while hard drives usually can store more than SSDs, due to their mechanical nature, they're usually slower and more prone to damage. Lastly, mostly found in handheld devices are eMMCs, which use similar technology as the SSD with the electrical charge. There's also external secondary memory, which isn't glued to its original device, making them more portable and compact compared to internal secondary memory. First is something you've probably seen before, a USB flash drive or a memory card. These also use the same electrical charge technology found in SSDs and eMMCs, and are commonly used for data storage in small devices like cameras and data transfer between devices. Next is also something that you've probably seen before, optical drives, also commonly known as CDs and DVDs. These use a laser to detect little pits or bumps on the surface of the disk, and these are used primarily to store files for mass distribution like movies, music, or games. There's also network attached storage, or NAS. Here, a separate computer stores files, and these files are then accessible through a network, like your home network, or an office or school network, or over the internet. Your school probably has an NAS for all students and teachers. Lastly, there's also cloud storage. This one is special because while the other forms of storage were more hardware-oriented so far, this one is more software-oriented. Cloud storage provides access to an external company's storage servers over the internet, meaning you or an affiliate organization doesn't store your data, and you don't have control over the hardware at all. This is an example of software as a service, and is one type of cloud computing. The term software as a service, or SaaS, refers to any service accessed over the internet via an app or a website. Users are able to access and enjoy all the features of the software, while the company behind the software maintains the underlying infrastructure of the software and its services. Chances are, you definitely use some sort of SaaS model in your daily life, whether that be watching movies on Netflix, creating something on Canva, buying something on eBay, or calling someone on Zoom. These are all examples of software as a service because these give you the service that they provide you without you having to manage any of the internal infrastructure of the application. There are other types of cloud computing as well, each with different access levels to the underlying infrastructure to the software from the user. SaaS provides the least amount of control, as we've discussed earlier, and Platform as a Service allows the user to create their own applications without having to manage its deployment, and Infrastructure as a Service allows the user to have full control over the application software with only the hardware being provided by a provider. You can think of SaaS like renting a hotel, PaaS as renting a hotel with no furniture, and IaaS as renting a plot of land where the land can be turned into literally anything. SaaS is useful when the user wants the functionalities of a software and nothing else. PaaS is useful when the user wants some level of customization for a software, and IaaS is useful for building a new system entirely from the ground up. Now let's move on to the concept of compression. Compression is simply the act of reducing a file size. This can happen in two ways. Lossless compression is a form of compression where data isn't lost at all. It's simply represented in a more compact way. This is done through run-length encoding, where repetition of data can be shortened. For example, say we want to compress this line of text. Instead of saying AAAA, BBBBBB, CCCC, we can simply say 4A, 6B, and 4C, which is much shorter and can easily be reversed back into the original version. Another method of compression is lossy compression. This is when small negligible details are removed from the file, making the file smaller and mostly keeping the original file intact. One key way it does this is through a process called transform coding and quantization, which decreases the overall precision of the file. An example is with this audio file. What transform coding does here is group similar amplitude spikes together. For example, it can group this region together, it can group this whole region together, and maybe it can group this region here as well. Then, these groups are represented as a single frequency or single amplitudes in the file, effectively making these a single amplitude instead of with these slight variations. So, instead of this would just be this flat little region right here. This could also just be a flat region right here. This could also be a flat region right here. Then we can use something like run length encoding again, which reduces the file size, but here, of course, some data will be lost permanently. So that's about it for A1.1, and now moving on to A1.2, data representation and computer logic. These will be the 4 sections for this subtopic. So let's first start by asking ourselves, how do we count? Obviously, we have the digits 0 to 9. But what if we want to represent a bigger number than 9? For example, the number 10. There's no digit to represent 10, so what we do is we just start over from 0 and add a new digit to the left, so a 1 right here. And this is the number system we use, mostly because we have 10 fingers. This is called decimal, and we call this a base 10 number system as there's 10 unique digits. But how do computers count? If you zoom way into your computer, you'll see that your computer is made up of tiny switches called transistors, and they're laid out like this. You can think of a transistor like a light bulb. It's either on or off. This means that computers can only physically store 2 digits, 0 for off and 1 for on. If they want to represent the number 2, they don't actually have the digit for 2. But they do the same thing as us when we run out of digits. They'd start over from 0 and then add a new digit to the left right here. So in this new number system, the number 10 actually means 2. This system is called binary, and it's a base 2 number system because there only exists 2 different digits. If we go back to our decimal number system right here, if you took elementary school mathematics, you'd know that this digit represents tens and this digit represents ones. And if we have any other digit, we'd have hundreds, we'd have thousands, etc. Well, if you see a pattern, it can actually be represented as 10 to the power of 0. This is 10 to the power of 1. this is represented as 10 to the power of 2. And this is 10 to the power of 3. So what I mean is, if we want to say the number 1110, this is the same as 1 times 10 to the third plus 1 times 10 to the 2 plus 1 times 10 to the 1 plus 0 times 10 to the 0. And this concept can be just transferred over to binary, except instead of 10 to the power of something, it's 2 to the power of something. So let's say we have this binary number right here. This digit would be 2 to the power of 0, or 1. This digit would be 2 to the power of 1, or 2. This digit will be 2 to the power of 2, or 4. This digit will represent 2 to the power of 3, or 8. So here, this is equal to 1 times 2 to the third plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 0 times 2 to the 0, which is just equal to 8 plus 2, which is equal to 10, or 10 in decimal. Hexadecimal is another number system, and it's base 16, meaning there's 16 unique digits. To fill in the missing digits, the letters A, B, C, D, E, and F are used to represent the numbers 10, 11, 12, 13, 14, and 15. Hexadecimal exists mainly as a way to make binary more readable to humans. So in hexadecimal, let's say we have the number 8A5. This digit will represent 16 to the power of 0. This digit would represent 16 to the power of 1, and this digit would represent 16 to the power of 2, much like the decimal and binary number system. Now let's go over how to convert between the three number systems. The main reason why hexadecimal is so useful is because binary and hexadecimal are super easy to convert between. You just have to know that every 4 bits in binary represent a hexadecimal digit. So let's work through this example right here. So I've split this binary number into groups of 4 for the sake of convenience. So what we do is we start from the right and we work our way through each of the group and find out which hexadecimal digit is these groups of binary representing. So this number is representing a 3 because this digit is 1, this digit is 2, this digit is 4, and this digit is 8. So we just know 2 plus 1 is 3. So this digit represents 3. For this group, we know that this value is 6 because if we just do the 1, 2, 4, 8 again, this digit represents 4 and this digit represents 2, and 4 plus 2 is 6. Same thing applies for this. This is 8, this is 2, so 8 plus 2 is 10, but of course 10 is represented by the letter A. So this binary number in hexadecimal would be represented as A63. Now let's do a slightly harder conversion, decimal to binary. So let's represent this decimal number into binary. So what I like to do is to represent the decimal number as a sum of powers of 2. Now what do I mean by that? What are the powers of 2? 2 to the 0, 2 to the 1, 2 to the 2, and so on. And if you've played 2048 before, this will be a piece of cake. This is just 1, 2, 4, 8, 16, 32, 64, 128, and etc. So we want to represent this number as a sum of these numbers. So let's do that. So first of all, what is the biggest number here that can subtract 169 and give a positive value? Well, it's 128 because 256 is too big. So 169 can be represented as 128 plus some value, and 169 minus 128 is just going to be 41. Now 41 can be decomposed again. So what is 41 represent? What can 41 be represented as right here? We have 32 because 64 is too big. So instead of writing 41 here, we can write plus 32 plus 9 because 32 plus 9 is 41. Again, this 9 can be broken down into 8 plus 1. So we can have 8 plus 1. And there we go. This is the sum of the powers of 2. We write this decimal number as a sum of powers of 2. And why do we do this? Remember, each digit in binary corresponds to a different power of 2. So if we have an 8-bit number here, this is an 8-bit number, we call this digit represents 2 to the 0, this digit represents 2 to the 1. So this digit represents, let's write it like this. This digit represents 1, this represents 2, 4, 8, 16, 32, 64, 128. So now we can just fill in the digits that these correspond to as 1. And what do I mean by this? Well, we see an 128 here, so let's put a 1 right here. We see a 32, so let's put a 1 right here. We see an 8, we put a 1 right here. And we see a 1, so let's put a 1 right here. And now we can just fill in everything else as 0. And there we go. This is going to be the binary representation of the number 169. And this goes the opposite way as well. If we wanted to convert this to decimal, we find out which decimal number each binary number represents. So this represents 128, this represents 32, this represents 8, this represents 1, and then we add them together to get back to the decimal number 169. So the final answer, 169, is equal to 10101001. Now let's go over the final conversion that we need to know. And sorry, we've removed this part so you can read this. This one is decimal and hexadecimal. So what I like to do is represent the decimal number as a sum of multiples of powers of 16. So what do I mean by this? Let's look at what I mean by this using this example right here with the same decimal number 169. So what are the powers of 16? We have 1, 16, 256. And honestly, we don't have to go anymore. So does 169 go into 256 first of all? No, it doesn't. So what this is telling us that this hexadecimal number will only have 2 digits because the third digit would represent 256, but since this number is not as big as 256, we don't need this extra digit right here. We only need these 2 digits right here. So now we need to fill in both of these digits. So of course 169 goes into 16, but then 169 minus 16 will just give us 153, which is still too big. So this is why we need to represent the number as a sum of the multiples of powers of 16. So what are the multiples of 16? Like, what I mean by that is, what is 16 times 1? Like, it's basically, I'm asking for the 16 times table. So what do we have? We have 16, 32, 48, 64, 80, 96, 112, 128, 144, 160, and so on. And let's just write 176 here as well. So 160 goes into 169, but 176 doesn't. What is 160 in terms of 16 times some other number? That's just going to be 16 times 10, right? So we need to have 10 16s in order to represent this number. So here we can represent this as 160 plus 9. Actually, let's do that again. We started too much. Now let's move on to the final conversion, decimal and hexadecimal. And this one is a little more tricky. We need to represent a decimal number as a sum of the multiples of powers of 16. So let's go through what I mean by that with this example, 169 again. So what are the powers of 16, first of all? It's 1, 16, and 256, and there's some more, but we can stop here for now. So first of all, is 169 bigger than 256? No. This tells us that this hexadecimal number will only be 2 digits, because this third digit represents 256. But we won't be using this digit because 169 is less than 256. So we can just ignore this slot. We'll only have 2 digits. Now, we need to find a digit here and a digit here. Let's do what we did like in binary. Let's do this little summation. So we want to represent it as a sum of multiples of powers of 16. But by this, I mean, what is a multiple of 16 that can go into 169. So firstly, let's draw the 16 times table. The 16, 32, 48, 64, 80, 96, 112, 128, 144, 160, and 176. What is the maximum number here that can go into 169? Well, it's 160, right? So let's represent this as 160 plus 9. We can also represent this as 16 times 10 plus 9, because 160 is 16 times 10. Now, what does this mean? Why have we put it like this? Because this tells us the digit that we need to put here. So what is 10 in hexadecimal? That's just going to be A, right? That's just A in hexadecimal. So we put an A right here. And the remainder here, 9, we can just put like that. So 169 is just going to be A9 in hexadecimal. And again, this is reversible. So if we wanted to convert this to decimal, we just look at this digit and this digit. This represents 16 to the power of 1, and this digit represents 16 to the power of 0. So if we want to convert this to decimal, we want to find what this represents, or what the value of this is, and what the value of this is. This value is just A times 16, which is 10 times 16, which is 160. And 9 is just going to be 9 times 1, so it's going to be 9. So 160 plus 9 will be equal to our original number, 169. And that's how you convert between the three number systems. Both binary and hexadecimal are used in many aspects of computing. Firstly, binary can be used to not only store numbers, but also to store letters. This is done by mapping a binary number to a unique English letter. This mapping is called ASCII, and it was later rebranded as Unicode, which incorporates Asian letters. So here you can see every single decimal number that's mapped to a single English letter right here. And we can just represent a word, for example, like hi, as 72 and 73. And of course, these would be represented in binary. Colors are also represented in binary. Every single color that you see on a screen can be written as a combination of red, green, and blue. By assigning a scale to each red, green, and blue, you can represent any sort of color you can see on this color wheel right here. So you may have heard of something called a color code. A color code is just a six digits with a hashtag right here. These digits represent red, these digits represent green, and these digits represent blue. This is because this color code is written in hexadecimal, and each red, green, and blue goes up to 255. And 255 is FF in hexadecimal, which is the maximum hexadecimal number, which can be represented in 2 digits. So if we have 2 digits for each color, this will total up to 6 digits. And with this combination, you can represent any color that can be visibly represented onto a screen. Finally, remember that audio file we looked at? Audio files just store how loud a sound is at a particular point, and that loudness is measured using numbers, for example, on a decibel system, and that decibel system is represented using binary again, using the number system. Binary is also used to store data. Every single storage device we talked about previously uses some form of binary. The electric charge technology in SSDs just mean if there is charge stored, it's a 1, otherwise it's a 0. For hard drives or magnetic storage, areas with high concentration of magnetism represent a 1, and areas with low magnetism concentration represent a 0. And this little device called a spindle is responsible for reading the different magnetism levels inside of this disk. For optical drives, the little bumps that we talked about on this optical drive, also called pits, represent a 1, and areas with no bumps or LANs represent 0. Everything that's related to computing and digital information use binary in some way to store information. Now let's talk about logic gates. If binary is how we store data, Logic gates is how we transform and manipulate that data. Logic gates are simply just logical operations performed on 1 or 2 bits, where some combination of input bits output either a 1 or a 0. There's 7 main gates you need to know, and this table shows 6 of them. Fortunately, every logic gate is quite intuitive to understand, and they will all be easy to understand after a few minutes. Each logic gate has an associated truth table, which is a table showing every single possible output for every possible combination of inputs. Using these, we can understand what each gate does. For example, the AND gate outputs a 1 if both input bits A and B are 1, which is shown here, where only this row where A and B are both 1 outputs a 1. The OR gate outputs a 1 if input bit A or input bit B is 1 or both, which you can see right here. A NOT gate simply outputs what the input is not. NAND, that's just the opposite of AND, which you can see these outputs are just the opposites of these. NOR is just the opposite of OR, which you can see right here. And XOR is slightly trickier, but it's just the OR gate with a twist. It's when it excludes the scenario where if both inputs are 1, it's 1, and instead if both inputs are 1 here, it's a 0. There's one more gate, and the hidden gate is called XNOR, which I'm pretty sure you can understand. It's just the opposite of this, and if you want to represent XNOR, it's just like these. You just stick a little dot on here. Now let's talk about Boolean algebra. We can represent all of these logic gates as mathematical expressions, which is called Boolean algebra. It can be quite unintuitive at first, but the key points are that the AND operation is this little dot or combining these letters together. The OR operation is this little plus sign. The NOT operation is just this little dash at the top or this little apostrophe. And the XOR is just the plus with a little circle around it. You could also think of AND as multiplication and OR as addition. Now let's combine logic gates together. Combining them together gives you logic circuits. A logic circuit is for when you want to expand out of the standard operations. Each logic circuit also has its own truth table, which we can find the outputs by tracing the logic circuit. To find the truth table for the circuit, let's start by labeling each gate's individual output as its own letter. So let's start by labeling this AND gate as C and this NOT as D. Now let's start making the truth table. So we can have A and B, those are our original inputs. Let's have C, D, and then the output X. So because we want to find all of the outputs for every possible combination of A and B, let's fill in the columns A and B with 0, 0, 0, 1, 1, 0, and 1, 1, which are the combinations that A and B can have. Now let's work through tracing this logic circuit. Let's start with the output of this AND gate. So C is just A and B, A dot B, which is just 0 because these are both 0, 0 because not both of these are 1, this is also 0, and this will be 1 because both inputs A and B are 1. Now let's do gate D. D is just the result of not to B. So not to B here is just going to be 1, 0, 1, 0. And now we can find the output X because X is just C or D. So C plus D. And here is going to be a 1, here will be a 0, here will be a 1, and here will be a 1. And there we go. This is the truth table for this logic circuit. The amazing thing about logic circuits compared to logic gates is that you're not bound to only 2 inputs anymore. The number of inputs can be as many as you want. Here we have 3 inputs, A, B, and C. Because we have 3 inputs, the number of possible input combinations will increase. To show this, let's draw another truth table. Let's draw first the columns A, B, and C. So what are the different input combinations here? Well, we can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And now we need to find the output x for each of these different combinations. So just like we did for the previous logic circuit, let's trace through this logic circuit again. And firstly, let's label each gate's output using another letter. So we'll call this D, we'll call this E, we'll call this F, and we'll call this G. So let's just make new columns D, E, F, and G, like so. Now let's work through this logic circuit. So D is just A NAND B. So what is A NAND B? That's just going to be the opposite of A and B. So A and B are both 0 here. Now that would normally output a 0 in the AND gate, but this is a NAND gate, so this is going to be 1. Same for here. This is also going to be a 1. This will be a 1 as well. This will be a 1 as well. This will be a 1 as well. But here, since an AND gate would usually produce a 1, here would be zeros right here. Now let's move on to E. E is just B XOR C. Remember, an XOR gate only outputs a 1 if only one of the inputs are a 1. So let's see. B and C. So here, both inputs are 0, so this will be a 0. Here, only one of the inputs are a 1, so we'll have a 1 here. Same for here. And both of the inputs here are 1, so this will be a 0. Here is also 0. This will be a 1, this will be a 1, and this will be a 0. Now moving on to F. F is just not C. So we can just do the inverse of C. So let's do 1, 0, 1, 0, 1, 0, 1, 0. Now let's work through G. G is just D and E. So we need to look at these two columns right here. So here, 1 and 0 is just going to be a 0. This will be a 1. This will be a 1. This will be a 0. This will be a 0. This will be a 1. This will be a 0. And this will be a 0. And now finally, the output X. X is just going to be G XOR F. So we can just look at these two inputs right here. So XOR, of course, means only one input must be a 1 in order to output a 1. So here will be a 1, here will be a 1, here will be a 0, here will be a 0, here will be a 1, here will be a 1, here will be a 1, and here will be a 0. And there we go. That is the truth table for a logic circuit with 3 inputs. Now let me introduce you to Karnaugh maps, or K-maps. A K-map is essentially just a truth table in 2D. It shows all the possible outputs for every possible input combination. If you don't understand what that means right now, don't worry, because you'll understand it after you see it. A K-map looks like this. Some inputs as rows and some inputs as columns. To start simply, let's draw a K-map for the AND gate. So we know that the AND gate, it only outputs a 1 when both inputs are 1. So in this square right here, A and B are both 0, so this will be a 0. Here, A and B are both not 1. A is 0 and B is 1, so this will be a 0. Same for here. On this square, both A and B are 1, so we'll put a 1 here. Looks familiar, right? This is kind of similar to the truth table for the AND gate. Now to expand K-maps for 3 inputs, we need to think slightly outside of the box. Since we can't have a 3-dimensional map for the 3 inputs, we'll instead smush 2 inputs together. So it will look something like this. We can put A as the rows here, but instead of having just B or just C for the columns, we can put the inputs B, C as the columns instead. Now, instead of having 2 columns, so just 0 and 1, we'll actually have 4 because there's 4 unique combinations of B and C. So we'll have 0 and 1 for A, and we'll have 0, 0, 0, 1, 1, 1, and 1, 0. And you write it 1, 1, and then 1, 0. That's just the traditional way to write the K-map. So now we can just fill in the outline for the K-map like so. And now to fill in this K-map, we just need to look back at this truth table, and we just need to match every input combination with the outputs. So for example, we have A, B, and C as all 0. Now what does that align with in this map? It's going to be this square right here because A, B, and C are all 0 here. So that's going to be 1. Now 0, 0, 1 is 1. So A is 0, B is 0, and C is 1. That's going to be this square right here. That's also going to be 1. Now 0, 1, 0 is right here because 0 is A, B is 1, and C is 0. That's going to be a 0. And now 0, 1, 1 will be this square because 0, 1, 1, that'll also be a 0. Now 1, 0, 0 is going to be this square, which is going to be 1. 1, 0, 1 is going to be this square, which is going to be 1. 1, 1, 0 is going to be this square, which is going to be 1. And 1, 1, 1 is going to be this square, which is going to be 0. The reason we use K-maps is because K-maps are useful for forming simplified Boolean expressions for logic circuits. These are the steps to doing it, and we'll walk through how to do it together. So step 1 is to look for all the ones in the map. So here we have the K-map that we drew for the 3-input logic circuit that we drew earlier. So step 1 is to look for all the ones. So that's going to be here, 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 and here. All right. Step 2 is to find square or rectangle groups of 2, 4, 8, etc. of 1. So etc. just means 16, 32. And those only apply for bigger K-maps, but here we can just look at this group of ones right here. So this is a square 2 by 2 group of ones. So now number 3, find the common inputs for each group of ones. What I mean by that is now let's look at what inputs go into each of these ones. So for this one, we have 0, 0, 0. For this one, we have 0, 0, 1. And here, let's just add some headings. These are A, B, and C. This one, we have 1, 0, 0. And this one, we have 1, 0, 1. Do we see any similarities? Yes. This B is constant for every single one of these combinations of inputs. So what we can do is we can write this as B prime. Prime, of course, meaning not, so this just meaning 0. So when we write B prime, we're actually referring to every single grid where B is equal to 0. So in this, B is equal to 0. For this input, B is equal to 0. For this input, B is equal to 0. And for this input, B is equal to 0. Notice how none of the other inputs or none of the other outputs have B equals 0. So by writing B prime, we're actually referring to this square grid right here. So now we write these common inputs in Boolean algebra, which is what we just did. It's B prime like this. Now step 5 is to repeat steps 3 and 4, linking the different inputs with OR gates. So we don't really have any other groups of 2, 4, or 8 of ones. We really only have this one right here. Now if lone ones are left, then write them out in Boolean algebra just purely. So for this one, how can you write it in Boolean algebra? This is just 1, 1, 0. Here's 1, and BC is 1, 0. So if we know that A is equal to 1 and A prime is equal to 0, how can we write this in terms of A, B, and C? So we have A, B, and C like this. So we can add an OR symbol here, and we can have A is equal to 1, so we can have A, B is equal to 1, so we can have B, and C is equal to 0, so we can have C prime. So we now have a Boolean expression right here, and we can label this as F equals to. Now F just means the output. And this combination, B prime plus A, B, C prime, is just referring to every single grid in this K-map that outputs a 1. So by looking at this, we know that any one of these inputs will equal a 1. And that's how we interpret the K-maps, and that's what K-maps are used for. Logic gates and logic circuits alongside binary are the fundamental building blocks of computing. For example, the ALU is built on logic gates, which essentially means that logic gates are the foundation for all mathematical and logical operations that happen inside of a computer. SSD's NAND technology uses logic gates, and the NAND gate in particular, to manage the flow of electricity and charge that eventually becomes stored as bits. The main point is, without logic gates, data would never be able to be changed, and all data would just be a lifeless hunk of ones and zeros. And that's everything for A1.2. Now moving on to A1.3, operating systems and control systems. So let's recap everything we've learned so far. Bits make up data. Bits are transformed through logic gates, which is then processed by ALUs so that CPUs can execute instructions alongside the rest of the computer, which keeps the computer running, which leaves us with a happy user. Binary is also used to represent letters, numbers, and colors, which also leads to a more comfortable experience with the computer. But there's a problem. Up until these points, everything is coded in ones and zeros. But us humans speak English instead, not binary. If this was the entire picture, we wouldn't be able to understand a thing a computer is saying. We need something to bridge the gap between the computer and the user. This is where the operating system comes in. The OS is a piece of software installed on every device, and its role is to manage hardware resources while hiding its complexities from the user. Now, what does this really mean? The concept of hiding complexities from the user is called abstraction, and is what allows people like us to use the computer without understanding binary. For example, the OS is responsible for providing a graphical user interface, or GUI, which provides an intuitive way for the user to interact with the computer. The OS is also responsible for maintaining security systems that defend against malware, such as Windows Defender. The OS also simplifies file management and disks. For example, instead of the user having to input all of the individual bits into the SSD to store a picture, the OS presents the SSD as a giant folder, and the user can simply drag and drop the picture into the SSD, which is really intuitive for the user again. But underneath the hood, the OS acts as sort of a conductor for the different parts of the computer. Firstly, the OS is responsible for memory management, where it tracks each individual memory location in RAM so it can effectively assign memory locations to processes. To facilitate this, memory is divided into little blocks called pages. These pages allow for programs to be divided in memory instead of in one long continuous lump of instructions. If RAM is nearing full capacity, the OS can also perform something called page swapping, where it can put the least used pages into secondary memory, which is slower to access but is way more abundant than RAM. The OS also manages the different external devices in the computer. When you plug in a keyboard, mouse, headphones, or any peripheral, the computer makes sure it works by installing the correct driver for it, which is just a small piece of software that makes the device work. Most importantly, the OS is responsible for allocating CPU resources to processes in RAM that need it. For this, a scheduling algorithm is used, which we'll get into right now. Now, a scheduling algorithm is just a method the OS uses to allocate CPU time to hungry processes. There's many different scheduling algorithms, but there's 4 that you need to know. The first algorithm is first come first serve, which gives all CPU resources to the process that came into RAM first. There's also round robin, which gives every process an equal amount of resources. There's also priority scheduling, which assigns each process a priority level and allocates the resources to whichever process has the highest priority. Lastly, there's multi-level queue leveling, which can be considered a hybrid of all of the aforementioned methods. This is when processes are put into groups, and those groups of processes can then be assigned another scheduling process, such as first come first serve or round robin. Each of these scheduling algorithms are used in different scenarios, and it's up to the OS to determine which of these algorithms will lead to the most optimized performance of the computer. The OS also needs a way to check on different things, whether that be the status of a process, a peripheral device, or a piece of hardware, so it can act on any potential issues or requests. There's 2 main ways to do this: polling and interrupts. Polling is when the OS repeatedly checks for any action to be taken, and interrupts are signals that are sent to the OS, usually an urgent event or request. The OS then makes the CPU stop its current action so that it can handle the interrupt instead. Both methods are ways that the OS communicates with other parts of the computer. Let's take an example of a keyboard plugged into a computer. So here's a little keyboard right here. Now the event here is when a key is pressed. With polling, the OS would constantly check if a key was pressed by the user. If it was, it would relay that information to the CPU to perform the corresponding action. With interrupts, an interrupt would be sent to the OS every time a key is pressed, causing the CPU to quickly deal with the interrupt every time a key is pressed. So which is better? Generally, interrupts have many key advantages over polling. Firstly, interrupts have a virtually immediate response time, as the CPU immediately acts on the interrupt when received. Polling, however, can incur some delay, as an event may occur between the interval that the OS checks for it. Interrupts also puts less strain on the CPU and consumes less power, as while interrupts only use CPU power when there is an event, polling requires a constant cycle of work done by the OS, which leads to some wasted CPU usage. These advantages are why interrupts are used in most real-world scenarios today. On the other hand, polling is simple to implement and is less prone to cyber attacks. This is because interrupts can be exploited by malicious programs to hijack the CPU. There are pros and cons to each method, but in the perspective of processing power required, latency, and electricity consumption, interrupts usually come out on top. For example, network communications prefer interrupts because networks want the least latencies possible when transmitting data. Small devices that use batteries, called embedded systems, prefer interrupts due to the efficient power usage. Your keyboards and mice prefer interrupts because, again, it's the option with the least latency. Real-time systems, like medical equipment, which require the lowest latency possible, prefer interrupts due to their strict timing requirements. Now let's talk about multitasking and how the OS manages multitasking. In computers, multitasking refers to the illusion of multiple programs being run at the same time. Unless your CPU has an ungodly amount of cores, this is impossible for a CPU. Instead, what the OS actually does is make the CPU switch between processes very, very quickly, making it seem like each program is being run smoothly from the user's viewpoint. This technique is called context switching, and what happens is when the OS tells the CPU to switch to another process, the last state of the CPU is saved and stored. So for a certain process, the PC will point to the memory location of the page in memory that the process is stored in. So this can be, for example, 50, and the different registers will all have certain values, and so on. When this process needs to be executed again, the CPU will load these values into the core and continue working on the process. Let's talk more deeply about processes and how exactly the OS distributes resources to the multiple processes to be ran in a computer. Every process has its own process lifecycle, shown here in this diagram. When a program is started on a computer, it's in the start state. The OS must now register this new program as a process and allocate memory to it. Once this is done, the process moves on to the ready state. This is a state given to processes that are in line to be executed by the CPU, since the CPU can only process as many processes at a time as it has cores available. When the CPU is ready to execute a process, the process moves to the running state, meaning the CPU is currently executing the process. When the process's allocated CPU time is up, which is determined by the scheduling algorithm, the process moves back to the ready state. While the process is running, it can also enter a waiting state, like this, meaning that the process is suspended until a specific resource that the process needs is freed. If the program is closed, the process is terminated, and the cycle ends. The OS is responsible for conducting all of this, making sure that each process gets its fair share of resources. However, problems can arise from this. The most obvious problem is starvation, where processes may not get enough resources to run properly. This can happen due to poor scheduling algorithms, if there are too many high priority processes that overshadow a low priority process, or when there are too many interrupts. Another potential problem is resource contention, where two or more processes in the waiting state want the same exact resource, but the resource cannot be shared between the processes. In such cases, the OS is responsible for allocating the resource to a specific process, leaving the other processes in the waiting state. Another similar problem is deadlocking, where two or more processes, process A and process B, want resources held by each other and are both in the waiting state. So in a diagram, it would look something like this, where this process A is waiting for process B, and process B is waiting for process A. Now this leads to an indefinite wait from all processes involved, as none of the processes can proceed until someone gives up their resource first, which of course will never happen because they're just waiting. Again, the OS is responsible for releasing deadlocks using the deadlock prevention methods. And that's about it for operating systems. And now onto control systems. A control system is a collection of devices that automatically regulates something based on a set of rules. This something is usually an analog trait in the real world, such as temperature, humidity, or infrared. These control systems form the basis for every smart device you see today, like for example, an automatic thermostat, which magically knows how to change your room's temperature to your liking. There's three key parts to a control system. First is the input phase, where analog data is retrieved. This is retrieved by sensors and turned into electrical signals by transducers. A key thing to note is that different types of sensors exist to retrieve different types of inputs. For example, temperature sensors, humidity sensors, or infrared sensors. After the input is retrieved, the data is processed. To do this, the data is sent to a controller, a small chip that makes decisions. A controller uses a control algorithm, which is a set of predetermined values that the controller uses as a basis to make decisions. When a decision is made by the controller, it sends the signal to an actuator, which is any device that makes an adjustment in the real world. Actuators also use a transducer to convert the electrical signals back into physical quantities. This process is repeated starting from the input until the control system is turned off. There's one more secret step called feedback, and it's when the output affects future inputs. For example, as the thermostat makes the room colder, the input sensor takes into account this change in temperature. Not all systems utilize feedback though, and a system that uses feedback is called a closed-loop control system, and a system that doesn't is called an open-loop control system. Here's a couple examples of control systems in the real world. For example, here's the thermostat I was talking about. There's also automatic doors, traffic light control, and washing machines. Each of these systems use the input processing output loop, but not all of these are closed loop systems. Let's walk through each of the specific details for each control system, including how the input is detected, how the control algorithm is set, and how the output is achieved. Firstly, for the thermostat, a temperature sensor detects the temperature in a room. The control algorithm values are set by the user, who inputs a temperature that the thermostat should keep the room at. To change the temperature, a heating system in the house, such as a house-wide furnace, changes its heat output to make sure the room is at a specific temperature. And as we've discussed, this system is a closed-loop system. For the automatic door, the input is actually detected by an infrared sensor. The door is meant to open when a human walks near, and a human emits noticeably more infrared to its surroundings. The threshold is when the sensor detects enough infrared, and if it does, mechanical motors slide both sides of the doors open for the guy walking past. This is an open loop system because the door's opening does not affect the amount of infrared the infrared sensor detects. In an automatic traffic controller, the times taken for traffic lights are determined by the number of cars on the road. To measure vehicle counts, an infrared sensor can theoretically be used again, but a radar sensor is more favorable due to its range and reliability for high-speed objects. The control algorithm is set by the city's traffic organization, who decides the maximum number of cars for a specific time for red and green lights. The output is the traffic lights themselves, specifically the times that different lights show up for. This is also an open loop system, as the traffic lights have no effect on the number of cars detected on the road. Finally, the automatic washing machine. A significant factor for washing machines is the water level, so a water level sensor detects this. The thresholds for water levels depends on the type of wash the user selected, so the thresholds are the preset settings associated with the user's input. To control the water's levels, a water dispenser and a water drainer is used. This is a closed-loop control system as well, much like the thermostat, because the output of water directly affects the water levels detected by the sensor. Now that's done for A1.3. Now for the final subtopic, A1.4, translation. This entire topic is HL only, but the topic is quite small and it can be fit all into one section. Firstly, let's talk about high-level languages and low-level languages. High-level languages are stuff like Java, Python, C++, and pretty much any mainstream programming language in the modern world. These languages are usually written in English syntax and are intuitive to learn for programmers. It also abstracts a lot of the hardware complexities associated with coding. Low-level languages are languages that have little to no abstraction from hardware complexities. The lowest form of low-level languages are machine code, which is just binary instructions that a CPU can directly understand. But a CPU can't understand a high-level language directly. To understand it, it needs a translator to translate the high-level language into machine code. There's two main kinds of translators, interpreters and compilers. An interpreter translates code into machine code line by line at runtime, meaning as an interpreter is translating, it also runs the code as well. A compiler, on the other hand, translates the code all at once into machine code before runtime, meaning that the code isn't directly run by the compiler. There's a few key differences between interpreters and compilers as a result. Firstly, error checking. When interpreters find an error, they stop translating and provide where the error was found. A compiler doesn't stop, but instead translates everything anyway and produces an error log of all the errors in the code. Secondly, when compilers finish translating, it produces an executable file for the program, while interpreters do not. Thirdly, interpreters are faster to start up than compilers. However, interpreters are generally slower than the executable file the compiler produces. Because of these traits, interpreters are usually used to test and debug code, while compilers are used to export and distribute finished products. But modern mainstream programming languages like Python and Java don't simply translate from the language straight to machine code anymore. Instead, what they do is compile code to something called bytecode, which is an intermediate representation of code. Bytecode can't be run by the CPU. Instead, it's run by a special type of interpreter called a bytecode interpreter. You can think of a bytecode interpreter as a virtual CPU that only executes bytecode. You know how traditional compilers produce .exe files, or at least on Windows? Now it's .py for Python or .jar for Java instead, which are run by each language's specific bytecode interpreter. If you've installed Java or Python before on your computer, you are downloading their bytecode interpreter so that you can run and edit these files. This bytecode model has several advantages over the traditional machine code model. Firstly, it is faster to translate to bytecode than to machine code, because with machine code, a lot of complexity arises from allocating memory, CPU optimizations, and looking up instruction sets. This makes translation faster for both the compiler and the interpreter, making program execution faster overall. Secondly, bytecode is more portable than machine code. Machine code has one major drawback, and that it's both hardware specific and OS specific, meaning if you try to run a .exe file on a Mac, obviously it won't work. Bytecode is much more portable because all someone has to do to run a .py file is to download Python's bytecode interpreter on their device, which supports installations for Windows, Macs, Linux, and even iOS and Android. One setback for bytecode, though, is that when everything goes right for machine code, the resulting executable file executes faster than bytecode. But this problem can also be mitigated using something called just-in-time compilers. JIT compilers can be used in conjunction with bytecode, and it compiles frequently run parts of the bytecode program into native machine code. While this compilation process might initially slow down the execution speed of the program execution speed can be faster in the long term. So now the question is, when do we use each kind of translator? We have interpreters, compilers, bytecode interpreters, and JIT compilers. When we're testing and developing code, both interpreters and bytecode interpreters are suitable, as they both have fast loading speeds and direct the programmer towards errors when they are found. In performance-critical applications, both compilers and JIT compilers are suitable, as they ensure the fastest possible execution of programs. And in cross-platform development of programs, bytecode interpreters and JIT compilers are way ahead, as this program can be run and developed on any device as long as the correct bytecode interpreter is installed on the device. And that's all for topic A1. My name is Jerry, and if you like what I do, then please subscribe and give this video a like. See you in part 2.